Don't go there yet. Don't go there yet. Okay, hello everyone. Welcome back to Comp 3430 Operating Systems. I hope that you are all having an excellent day. Snowing yesterday. It's snowing yesterday, and that was very much a Michael Scott no moment for me when I saw that snow coming down. But I was notified, Rob sent me a link to a Reddit post on the U-Manitoba Reddit where someone has announced that they saw a goose. And so I feel like spring is coming. Spring is definitely happening. Did you really? Okay, good. Thank you for confirming goose sightings. Yes, I'm really happy about that. I'm happy about it being spring. I'm not happy about the geese coming back. Pigeons too. Well, they never go away. They're just always here. Let's talk about operating systems. So I've got two things that I want you to be able to do today. I want you to be able to write code that uses pthread mutex lock to be able to protect a critical section. And we kind of did a little bit of this already last class where we were looking at the list insertion stuff and trying to make decisions about where we could put these locks, what kinds of characteristics they're going to have in terms of performance. And what effects they're going to have in general. The main thing that I want us to be able to do today is I want to be able to identify code protecting a critical section that would result in deadlock, and then propose solutions that would avoid and or prevent said deadlock. So today what I want to do is spend some time taking a look at that code that's in the thread management repository that's called deadlock.c, and then try to answer some questions about those 4 conditions for deadlock. So trying to think about things like mutual exclusion, hold and wait, circular wait, and no preemption. Thank you. Yes, no preemption. I want to be able to think about each of those things and try and make decisions about if all of those things hold, and then ultimately whether or not this code could potentially deadlock. Before we get to that, though, I actually want to talk about some code that is code that I shared with you for this assignment. So I'm going to change directory not to report cards. I'm going to change directory to Comp 3430 2025 winter lectures. Week 8, lecture 21. And I want to look at some code here that's called process race condition. So there were a couple of people posting on the forum some issues that were showing up with the code that I had given out where there were assertions failing, specifically related to part of my code that was reading directory entries from directories. And the assertions that were failing were related to, basically, I would keep track of the state that I'm in as I'm reading directory entries from a directory. So I will read a file directory entry, and then I'm going to change the state that I'm in to be the next thing I should expect to read is a stream extension. Once I read the stream extension, then the next thing I should expect to read is n file name entries, where n is greater than or equal to 1. And then once I've read through all of those file name entries, I should then switch my state back to the next thing you should expect to read is a file directory entry. And I was seeing these failures happen, and I was asking these students, because there were 2 in particular that were having this problem, to go through these wild exercises of making sure that we're using the same library, the same version of the compiled code that I gave out, and the same volume. Because the problem that I was seeing was that they were showing me screenshots of command sequences that would cause this assertion to fail, and then I would get a copy of their code and transfer it to Aviary, and I couldn't make it happen. In fact, what I would get is like them printing out command not found, because the code that I wrote was returning this file doesn't exist. But they were trying to open things like /head, which is absolutely there. It's 100% there, but my code was saying, no, it's not there. And I couldn't figure out what was going on. I could not figure out what was going on. I didn't understand why they were getting these assertions failing, and I wasn't able to reproduce it. And I was eventually able to figure it out, and I want to share with you what was going on because it is so closely related to race conditions and threads and stuff that I think it's important. It's also humbling for me because it's kind of like I wasn't expecting people to use the code that I gave them in the way that they were using it. My hint about this is that when I was working with my NQP exFAT code, I never called any of the functions after I called fork. I never called any of the functions after I called fork, and these students did call those functions after they called fork. That is not the wrong thing to do. To be clear, they didn't do anything wrong. They're not doing anything wrong. It was just an assumption on my part because of the way that my brain works. I did it this way, and I never saw this problem in my code because I didn't do it the same way that they were doing it. And so I reduced this. I wanted to reduce this to a very small example. And I've reduced it to a very small example here that doesn't involve exFAT for realsies at all. But it involves reading a file, which is what we're doing with exFAT. And this is the minimal example that I came up with here. So I've got my code here on the side that demonstrates this. exFAT.txt is the name of the file that you see on the left side of my screen right now. And what I do with this is I read 20 bytes. All of these lines are identically sized. They're all exactly the same size, kind of in the same way that these directory entry types are all the same size. They're all exactly the same size. I replace the new line character potentially with this null byte, so I get rid of the new line character that happens to be on that line. I print it out with the process ID that got the line from the file descriptor. And then my process here is to do approximately what I'm saying. If I read a file entry, I read a line that starts with file and then a period, then I should assume that the state that I'm in right now is state 0. I haven't read anything yet. So I should start by expecting that this is the state that I'm in. This is the first thing I'm reading. And I should further assert that there are no file names to be read anymore. I've either read them all or there were none in the first place for me to read. So this is like the first file entry that I'm seeing. This is the very first file entry that I'm seeing. As soon as I see that, I'm going to switch my state. Now I'm in state 1. Once I'm in state 1, I should expect to see the stream extension next. So I've read a file. I know that I've read a file because I'm in state 1 now. And so if I've read a stream extension, then I can assert that I am in state 1. I must be in state 1 to have read this line that contains stream extension. I should further still be able to assert that I have no file names to read because there haven't been any file names or stream extensions read yet. I am currently reading the stream extension. If I am able to confirm that those things are true, then I'm going to change my state to state 2. The next thing I should expect to see are file name directory entries. And I should expect to see n of them. So however many I've got, I've written here stream extension and then a number that indicates how many of these file names I should read. And then I use this a2i function to turn the string into a number. And then after that, my approach is I should assume that as I'm reading these file name entries, I am in state 2 and that I have more file names left to read. As I read them, I decrement file name. This is pretty much what my code was doing for entry sets, but it's boiled down all the way to like read lines from a file that matches this thing. If I've got into state 2 and I have no file names left, then I switch back to state 0. The next thing I should expect to see is a file directory entry. In my file here, I've got file stream extension 1, file name, file, and then data. So this is some cluster that's full of other files data, and then more directory entries, and then more data, and then more directory entries, and more data. I'm going to run this right now with this line in particular commented out. Line 17 is commented out. And I'm going to run it, and it runs to completion. None of the assertions ever failed in this code, which is what I expected to happen because it's this nice state machine that's going through each of these different states to get me through and verify that I'm in the correct state as I'm reading things. I'm going to add this line back. Child is equal to fork. I'm going to make process race condition, and I'm going to run this. And it fails almost immediately on assertions. What's happening here is just open read only. Process 1 is on the left and process 2 is on the right. Process 1 reads file and stream extension. Process 2, when it reads, is reading from the same file descriptor. The open file table is duplicated across these two processes. So when process 2 gets to run, the first thing it reads is file name. It's not in state 0, and so it fails its assertion. The first thing that I read from this was file name. That's not the state that I should be in right now. So if we've got these two processes that are running at the same time, they're both calling read on the file descriptor that was shared across all of the function calls that I had. And the two processes are messing each other up. As I was stepping through this code, the actual exFAT code with my debugger, what my observation was that I would read a file, and then I would read like a bunch of things that are not actually directory entries because the other process had read the next thing from it. And then my process got control back again, and it's stuck out in the middle of nowhere right now. And so if we take a look at this code, what we can see, this output here is process ID with 78 that ends with 785 read the file, ends with 785 read the file name, and then 786 comes along and it read the stream extension. So now 786 is going to fail because it's not in the right state to have read the stream extension. And then process ending at 785 is going to fail because it will not have read the stream extension at all. It will just have had this thing get skipped on it, and which is why it's reading the file name there immediately after the file. So the order of output is kind of messed up here, but these two processes, because they're working with the same file descriptor, they're interfering with each other. They're causing these things to happen. And so my code with exFAT.c was also failing for exactly the same reason. Process 1 would read some file directory entry. Process 2 would then start reading a file name directory entry because that file descriptor had been modified by the first process. And then it would run into this strange, this kind of an output here. My solution to this was, instead of keeping a file descriptor at the file scope, put the file name of the volume at the file scope, and then stupidly open it for every time we call read and for every time we call open, which is not ideal. It's not exactly ideal, but it's functional, and it solves the problem that we have. Now we'll have two separate, completely separate open file table entries for the two processes that are running right now, and it will solve that problem. I'm going to put this code up on GitLab. I didn't have time to do it before class today, but I will put it up there if you're interested in seeing it and trying to run it on your own to see what it looks like. But I thought I would share that with you, partly because it's like, again, this is a humbling experience of, oh my God, this is not actually working and I don't fully understand what's going on. But also I took the time to try and figure it out, and I wanted to share that with you because I don't know. I found that thrilling. As stressful as it is for somebody else to say, hey, your code's broken, it's nice to be able to figure out what the problem was with it. Yeah, all right. Okay, so what I would like to do first is I'd actually like to start by doing a little quiz. So I'll leave this up for a couple of seconds. If you're joining right now and you've got a question about the code that I just posted, I'm very happy to answer any questions. But like I said, I'll post it up on the course webpage or on GitLab after class today. All right, I'm going to switch over to Mentimeter here. And I'll wait for about 5 more seconds, and then we'll get the quiz started. All right, the code should stay up there, so if you haven't quite joined yet, you should be able to keep joining after the quiz is started. Here we go. Okay, awesome. Yes, node scope was the one that would maximize concurrency. As I was looking at these answers, I do want to call this one out specifically, that this technically is correct. A function scope lock will maximize concurrency in that nobody ever gets locked out of anything and everybody gets to run all the time. Technically, that's correct, but I suppose the constraint of the question here is, and also results in a correct list, and also results in the correct behavior for what we wanted. So node scope 100% is the one that maximizes concurrency. So good, awesome. Here's the next question. All right, okay. So yeah, voluntary preemption definitely is the one that's not a condition for deadlock. I gotta be really honest, I don't like these like tricky questions that negate the thing that we're asking for, like picking the one that doesn't fit. Pick one of these things is not like the other sort of thing. I don't really like those, but here it is anyway. Voluntary preemption. Voluntary here is pretty much just like, yes, I am willing to give up the thing that I have voluntarily. Here you go. It's yours now. You can do whatever you want with it. That actually is something that could break deadlock for us. That's something that could possibly break deadlock for us. So it's not a condition for deadlock itself. No preemption here, remember, is once I've got it, you cannot take it away from me. I have it, I hold it, you can't have it, you cannot have it. Hold and wait is I've got one thing and I'm waiting for the other. Circular wait is two different people or two different things waiting for the opposite. Mutual exclusion here is once one thing has acquired it, then nobody else is going to be able to acquire it at the same time. So voluntary preemption is definitely not a condition for deadlock here. Okay, all right. Can deadlock happen with only one lock? The answer is no, it can't. If you only have one lock, then you've already broken both circular wait and hold and wait. If there is only one lock, there's only one lock to hold, so you don't have to wait for anything. You can immediately proceed with whatever it is that you're doing and then release the lock and then kind of end. So deadlock can't really happen with one lock. I'm going to add one tiny thing to this. Technically, oh my gosh, I'm like putting technically around this emphatically. Technically, yes. If you acquire a lock and then try to reacquire the same lock, then you will technically go into deadlock with yourself. Technically. You acquire the lock and then you try to acquire it again, you already hold it, so you'll have to wait until you release the lock. Technically, that could happen. I'm confident that pthread mutex lock is aware of this condition. You already hold the lock. I'm not going to let you try to lock it again because you already have this lock in the first place. Technically, it can happen, but no, generally it cannot happen. If there's only one lock, we can't have circular wait and hold and wait. Clippy. All right, okay, so Adrian's way to the top here. Let's keep moving on. There's 2 more questions that I've got. This one is going to be about lock implementations. Awesome. Yes, great. Thank you. Yeah, absolutely. It's a queue. I love the idea of a ticket lock. I think it's so cool, this idea of this thing that is implicitly implementing a queue. We're literally not writing the word queue in this anywhere ever. We're incrementing a counter and then letting different threads of execution have a different value in that counter. But it's a lineup. It's a first in, first out. It's the first thread that tries to get the ticket will get the lowest number. The next one gets the next highest number. The next one gets the next highest number. And we're ultimately implicitly implementing a queue with this thing without actually implementing a queue. I think that's awesome. I think that's really cool. So yes, it's a queue data structure. Here's the last question for the quiz. There's going to be a couple of things after this that we're going to use this Mentimeter for, but this is the last question for the quiz. Excellent. Yeah. Okay. So I mentioned this in passing, and I wanted to make a point of coming back to this. I wanted to actually have the time to talk about this. So here it is. Deadlock is happening with processes and pipes in this specific circumstance where we're reading and writing ends of the pipes. When I call read on a pipe and I block, I have effectively acquired a lock. I have effectively acquired a lock, and I'm waiting for that that lock to be given to me, or I'm waiting for this lock to be given to me. When I write to the end of a pipe, I'm effectively releasing the lock, Holding pipe ends open is kind of implicitly holding on to locks, holding on to these resources that we have shared between these different processes. So reading and writing the ends of a pipe and holding the ends of the pipe is kind of synonymous with this idea of what we've got with locks, acquiring them and releasing them in terms of the behavior of blocking and stuff like that. Yeah, okay, I really like that. Okay, so here's our end result. All right, congratulations, Adrian. And congratulations, John Cena. Thanks for showing up again. Kool-Aid Man John Cena. Okay, so we're going to come back to this Mentimeter. So if you've got your device open, please keep it open. What I want to do is I want to take a closer look at this deadlock.c again, and I want to be able to answer some questions about the 4 conditions for deadlock to try and decide whether or not this code can deadlock. So if you want to get a copy of this up on your own screen, you can find it in that repository, or if you want to have it in your own terminal, you can clone this repository. I'm going to pop back over to my terminal here, and I'm going to change directory back to my root directory here. We're in A02 right now, lecture 22, lecture 21, and thread management. And the file that we're looking at here is called deadlock.c. I don't want to dwell on everything that this code is doing, but I do want to very quickly remind you that the main function is responsible for setting things up for us. So this is where we're actually launching the threads and where we're picking the arguments for the threads, so the things that are going to get passed to the threads themselves. The actual work here is done in this deposit function, And the deposit function is locking a critical section. It's locking a race condition with locks. The critical section and the thing that we are ultimately trying to lock are the balances of the accounts. So these two lines right here, these are the ones where we're actually having this race condition, this critical section where multiple threads of execution operating on the same accounts would cause problems for us in the same way that we were losing nodes and losing ads. If we had two threads of execution entering these two lines and operating on the same accounts, we'll have a race condition here because these are not atomic operations, the statements that we've got. So this is the code that we've got. I'm going to leave this up on the side, and I'm going to bring this back. I'm going to open that on the side here. I'm going to set this up after we get to the question. The first question that I have is, given this code that we've got right now, mutual exclusion is one of the conditions that we have for deadlock. And so my question for you is, make an assertion here. Do you agree that mutual exclusion is enforced in deadlock.c in this code here? Or do you disagree that mutual exclusion is enforced? I'll give you about 5 seconds or so to answer this question, to give you a little bit of time to think about it. Okay, so I'm going to say that we all pretty strongly agree that mutual exclusion is enforced here. And I am going to agree with you. I'm going to agree with you in 2 different ways. The first way that I'm going to agree with you is that we can make an assumption that pthread mutex lock correctly implements locks. We can make this assumption that calling pthread mutex lock on a pthread mutex t will actually enforce mutual exclusion. It will block threads that are waiting for the lock, and it will allow exactly one to enter the critical section. We can assume that that implementation is correct. We can make that assumption. The other way that I'm going to agree with you is that the placement of the locks, where we put these lock objects on the accounts, this balance mutex itself, we are effectively enforcing mutual exclusion to say that only one thread of execution will be allowed to check the balance of the from account if it is able to acquire the lock. If some other thread has acquired this lock, then no other thread of execution is ever going to get to this point. It will never be allowed to proceed to that point until that lock has been released by the first thread that got it. So in that sense, only one thread of execution will be operating on from at a time. So we have enforced mutual exclusion here. Does that make sense, everybody? Okay. Our next condition for deadlock was no preemption. Again, agree or disagree, has this code effectively enforced no preemption? I'll give you 5 or 10 seconds to answer. All right. Okay, so I see that we've got we've got a bump here. We've got a bump kind of in the middle. There's people that agree and there are people that disagree. And it's skewing now toward disagree. I think that this idea that we disagree might be related to this part. I think. Please feel free to correct me if I'm misinterpreting your understanding of this, but I think that that's what people are picking on right here, is that we are unlocking here if we are not able to validate the transfer. In this case, I'm going to say that no preemption is true. There is no preemption here. A thread might be preempted. I will say that. A thread might get preempted. And when I'm using that word, I mean in the hardware sense, in the context switching sense, in the operating system has to respond to these interrupts from the hardware and make switches between threads of execution. There is preemption between threads. But once pthread mutex lock is called here, the thread that gets the lock, while it may be preempted from the CPU, it will not have the lock taken away. If it has the lock, it has the lock. Our OS actually has no idea what balance mutex even is. As far as our OS is concerned, balance mutex is some random byte in the heap. That's all it knows. There's data in the heap that this process is referring to, but our operating system doesn't know that it would need to remove this lock from the thread of execution at all. It doesn't know that it exists. So pthread mutex lock, again, is correctly implemented here. The thread may lose control of the processor and get kicked off for some other thread, but even while it's kicked off of the processor, it's still holding the lock. No other thread of execution will be able to acquire the lock while it has it. Does that make sense to everybody? We all on the same page about that? Are there any questions about no preemption? Okay, again, strong emphasis, yes, there is preemption of threads, but we cannot preempt the lock itself, the resource that we're holding on to here. Here's our next condition for deadlock, hold and wait. Once we've acquired a lock, once a thread of execution has acquired a lock, do we hold and wait for another lock if we are not able to acquire the second one? I'll give you 10 seconds or so to answer this question. All right, okay. So we are now skewing further towards strongly disagree. Hold and wait, and I'm believing that we're skewing towards strongly disagree because of this line right here. I believe this is why we are skewing towards strongly disagree. However, I am going to say that hold and wait happens here. This code does hold and wait. The hold and wait is happening here. Once we acquire this lock, we have locked the from account. We will voluntarily release that account lock, but only under certain circumstances. The certain circumstance is that there is not enough money in the account to do the transfer in the first place. If there is enough money in the account, I'm going to proceed to line 55 here. I hold the from lock. And if someone else holds the to lock, I'm going to get blocked, and I will wait here. I will hold on to the from lock, and I'm just going to wait while the to lock is held by somebody else. Once I'm able to acquire that lock, I will unlock them both after I've done the transfer. But while the to lock is held by someone else, I will continue to hold on to this one. I will just stop here on line 55. I will hold on to the from lock, and I will not release it until I've acquired the other lock. So hold and wait is enforced in this case, or it's true for this code that we've got. This unlock in the middle, this is a red herring. Does everybody know what that idiom means, red herring? Does anybody not know what red herring? Okay, red herring is, it's from a book from like England in the 1600s or 1800s or something. I don't know. I don't know what the book is called, but there's a part of the story where there's literally a reference to a red herring, a herring fish. And it's meant to be like, hey, look at this red fish. It's important to the story somehow. And then later you find out it has nothing to do with the story at all. It was just like this thing that shows up that you're supposed to pay attention to, and it's not that. So this is a red herring. We look at it and we see, yeah, obviously we're giving up control of this lock. We are releasing it. We're not holding it while we're waiting for something. But we are, in fact, once we get to line 55 here, we are holding and waiting. We are holding onto the lock that we previously acquired and waiting for this one to show up for us. Does that make sense, everybody? Okay. Here's our last condition for deadlock, circular wait. Do you strongly agree or strongly disagree that there's a condition where we could have a circular wait between two concurrently executing threads in this code? I'm going to give you like 10 whole seconds to think about this, maybe even 20 whole seconds to think about this before you respond. And before we start thinking about this, okay, so our response here is again very like lumpy. There's not much in the middle. People either very strongly agree or very strongly disagree. But we are skewing more towards strongly agree than strongly disagree. This code right here, as it is stated, with what we can see right now, there's no obvious circular wait situation. There's no obvious circular wait condition here in the code that we see. I will acquire the from balance, and then I will acquire the to balance. If I have thread 1 executing, it will acquire from, and then it will acquire to. Thread 2 is executing, it will acquire from, it will acquire to. There's an order of operations here, and it can only happen in this particular order. There's no situation where one thread is waiting for the other thread to release a lock in this case, or at least not interminably. They're not waiting on each other to release locks. I'm going to move down back to my main function here. And I'm going to highlight these two lines right here. And in fact, I am going to go even further, and I'm going to highlight this section. And I'm going to go even further than that, and I'm going to highlight these two numbers right here. The deadlock code itself, there's no obvious way that this deadlock code in this deposit function will have this circular wait condition based on the names of the variables that we're looking at here. But when we are creating these arguments between the two of them, this is from. Account 1 is from for thread 1. Account 2 is from for thread 2. Account 2 is to for thread 1. Account 1 is to for thread 2. And so let's go back up to the deposit function here and imagine that we've got these two threads of execution. Thread 1 is transferring from account 1. Thread 2 is transferring from account 2. Thread 1 gets to go first, and it's able to acquire the lock on account 1. Thread 2 gets lock on account 2. They might get interrupted in between this, but they're each going to acquire the lock on those two separate accounts that they've got. Thread 1 will get to go. it's going to run and check, okay, there's enough money in this account to do this balance, so I'm not going to unlock it. Thread 2 will get to go, there's enough money in this account, so I'm not going to unlock the lock that I've got. Thread 2 is going to get here, and it's going to try to get a lock on account 1. It will get blocked. Thread 1 already holds that lock. Thread 1 tries to lock account 2. This is the 2 account in my argument. It gets blocked. Thread 2 already holds that lock. And now we're stuck. Now we are deadlocked. Neither of these threads are going to be allowed to proceed because they're both stuck waiting for the other one to release the lock that it currently holds. So the code that we've got here, in terms of the names of the variables that we've got from and to, leads us to believe that this is going to be okay because they appear to be different things. But the actual arguments that we're passing to these threads of execution sets up this condition where we have this potential circular wait between the 2 threads of execution. I'm going to write this, I'm going to zoom out, I'm going to change to this directory. I'm going to make this code, and I'm going to run deadlock, and like, I cannot make this happen. I can't, I don't want to run make, I want to run deadlock. I can't make this happen. I really didn't think I would be able to make this happen. Oh my God, this is just like a red letter day for me. I really genuinely did not think I could make this happen. This is such a rare condition, and I actually really want to make sure that this is not just spinning infinitely right now. Okay, OBS is using 100% of my processor. That's totally fine. And deadlock is running. I mean, it's sleeping because it's waiting for locks. They're both waiting for locks. Oh gosh, I'm overjoyed that I was able to make this happen. I really can't believe it. Like, I actually cannot believe. It is so unlikely for this to happen that I cannot believe that it's happening. It's mind-blowing. Okay, this is a rare event. You saw that I ran it about 15 times before this actually happened. Now I'm going to get to the next class. I'm going to try this, and it's not going to happen. The circumstances that we had to have for this is that the first thread of execution had to be able to run line 44 and then get interrupted so that the second thread of execution could run line 44. And while these are not atomic operations, there are vanishingly small numbers of instructions here in terms of switching back and forth between these 2 threads of execution. So I guess the last question that I have here is, based on all that, the code in deadlock.c can deadlock. Please answer maybe or definitely no. And I don't really see the point in waiting too long for this, because obviously the answer is maybe. Yeah, the answer is maybe. The really important part, and I want to stress this a lot, that oh no, somebody should not have picked anything less than 5.0 here. I'm writing the words maybe here. And I'm also writing the words guarantee no. We've got 2 options with deadlock. I can promise you that it will never happen, or I can say it might happen. But I cannot promise you that it's going to happen. And I'm like, I don't know if it was clear by my response here. I cannot promise you that it's going to happen. I can't promise. It's something that's just going to happen sometimes, maybe. So my last question about this then, and I'm going to zoom back in here, and I'm going to bring this back over to the side once I get to this last question, is how do we fix it? Here's my code. I'd like you to give me some kind of response. Doesn't have to be anything huge or earth-shattering, but how do we do it? Write better code. Yeah, write better code. That's a good suggestion. Don't fix it. That's not an unreasonable response. It's funny, but it's not unreasonable. Don't fix it might be, Mom, look at this code I wrote. And then Mom will run it, and then she'll say, oh, I get stuck sometimes. And then you say to Mom, don't worry about it. Just close it and start it again, and it will be fine. That's not a terrible solution. It's not actually fixing the problem, but it's not a terrible solution. Add another lock. Okay, yes, yeah, add another lock. That seems like a real stupid thing to do because more locks just got us into this situation in the first place. Add another lock. Break one of the conditions for deadlock, yes. Adding another lock might break one of the conditions for deadlock for us. Clone the variable, so duplicate. That one I'm going to have to ask for further clarification on if you're willing to give it. Which variable do you mean to clone?
If you have a duplicate variable, the actual variable wouldn't be locked, so I think the concurrent threads wouldn't fight for the same variable. They would be actually using a different variable that's the OP scope.
So duplicate the lock itself or duplicate the bank account? Okay, duplicate the bank account. That would be an okay idea to duplicate the bank account. So within this code, don't bother trying to acquire these locks. Just make copies of the bank account that you're working with.
Copy of the bank account and then lock the copy.
Lock the copy, okay. The problem that we're going to have with making a duplicate of the bank account and then locking the copy is that because it's our duplicates, the lock is also something that can only possibly be held by us at that point. And so we'll have two concurrently executing threads of execution that are each independently locking their own copy of that bank account. And then writing it back, we're still going to have the same problem when we get to this point here, because we're going to have to make changes to the original bank accounts when we have to complete the transfer effectively. If we just lock the copies, we're just effectively having function scope or thread local locks. So every thread of execution is going to get to run its own lock. Does that make sense? Okay. Watch a movie and forget everything. Yeah, make the function atomic. Okay. So there's a couple of things that we could do for this. One is, yeah, add another lock. One thing that we can do is add a new lock right here. Add a file scope lock and acquire it before trying to acquire any other locks. Declare this at the file scope and make it so that this function cannot be executed concurrently. That would solve the problem. We would not be allowed to even begin to acquire the locks on from and to if we can't even enter the function, because somebody else is currently running code in this function right now. The problem with this is that it serializes all transfers. We can only literally do one transfer at a time. No matter what accounts we're looking at, they're always going to be locked and blocked if we cannot conduct transfers between these things. Make the function atomic. That's an excellent idea, and I think that's ultimately what we would do by adding this additional lock, is to do something like that. I'm going to pop back to my slides for now, and I've got a couple of options here. One is to try putting that lock in our transfer object, but that's going to be kind of what you're describing with duplicating things. It becomes a thread scope lock, and so the lock is always going to be acquired because the thread of execution that's running the transfer is just guaranteed to get it. We could add that file scope lock, and that breaks the hold and wait and the circular wait, but it's going to serialize all the transfers that we're making. Another option is to sort the accounts. And that means either literally sorting them on the address that they have. So sorting them in order because each of these addresses is going to be unique, or adding some property to the account that's like an identifier that you can sort, and then changing the arguments so that we're doing the correct negation of the transfer between the accounts after we've done the sorting operation, and it becomes kind of complicated to do that. Another option is to use this function try-lock, and I've again made this mutext mistake. I don't know what my fingers are thinking when I'm typing this out, but they always want to put a T after mutex. This is an okay thing. It can break that hold and wait condition, but it can lead to this circumstance of live lock, where we have try-lock, release, wait, try-lock, release, and we just get stuck in this cycle of these two different threads constantly trying to lock the next lock. At this point, you should be able to identify code protecting a critical section that would result in deadlock, and you have now some solutions that would avoid and or prevent said deadlock. Thank you all for coming out, and I will see you all on Friday. Bye, everyone.